Hello, everybody. My name is Tomer Lange. I'm a PhD student at the Technion. Today, I'm going to present a work of mine, which is joint with Professor Sefi Naor and Professor Gala Edgar. And our subject is offline and online algorithms for SSD management. A short introduction, write amplification reduces the endurance of an SSD and harms its performance. Hence, it is important to design algorithms that minimize write amplification. However, most existing algorithms are based on experimental evaluation. In this work, we address this problem from a theoretical perspective. We can think of an SSD as a table in which each column represents a block and each cell represents a physical page, and logical pages to be written are written to clean physical pages in the SSD. In the first part of our research, we concern myopic algorithms, where a myopic algorithm is an algorithm that has no information about the future. We conduct a worst-case analysis of the performance of the greedy algorithm, and we also obtain a lower bound for deterministic algorithms and a lower bound for randomized algorithms. Our approach. A key notion in our approach is the death time. The death time of a page is defined by the time it will be accessed next. It was shown that ideally each block groups pages with consecutive death times. This way, blocks are invalidated sequentially and no rewrites needed. Unfortunately, we mostly cannot maintain such an optimal layout. So it is still unclear which block to clean and when, and where to place each page. The offline algorithm. Our placement strategy works as follows. We place new pages sorted by their death times until no clean slot is available. For example, if we have 2 clean blocks, 4 slots each, we look at the next 8 requests. Each request is represented by a green square. The number within each square represents the death time of the corresponding page. So we place the pages in the slots such that pages that are placed in the same block have consecutive death times. The victim selection. Here we have 2 options. If completely invalid blocks exist, we clean all of them. Otherwise, we reorder all pages by their death times. We can show that this algorithm is very efficient. In particular, for any request sequence, its write amplification is not greater than 1 plus epsilon, where epsilon is a small additive factor which depends on the device dimensions. We now augment the online setting, assuming that each request arrives with a predicted death time. To apply the same placement strategy, an additional memory is required. We use this memory as follows. When a request arrives, instead of writing the page immediately in the SSD, we write it to the memory. We aggregate pages in the memory, and after the memory becomes full, we move the pages to the SSD such that pages are ordered with respect to their predicted death times. We can show that the performance of this algorithm improves as the prediction error decreases. Furthermore, this algorithm is never worse than the greedy algorithm. Experimental evaluation. We compare the 4 algorithms, greedy, hot, cold, online, and offline. We use 2 synthetic traces, one taken from uniform distribution and the other from zip distribution. It can be seen here that both online and offline algorithms achieve write amplification, which is close to 1 on the uniform trace. On the other hand, both greedy and hot cold achieve write amplification, which is much higher. On the zip trace, all algorithms achieve lower write amplification. The reason is that in this case, the memory is more efficient as a cache since the distribution is more skewed. Still, we can see a gap between the performance of our algorithms with respect to greedy and hot cold. Please refer to our full version paper for additional results, including prediction errors, real traces, and so on. Thank you for your attention. I'm here for any question. Bye-bye.